In addition, we will pick up from where we left off last time, the end of chapter 1, and go to chapter 2 for UML. So I'm going to share my screen. Where am I? All right, let me adjust this so I get better. All right. How's that zoom in? All right, as I recall, we left off, we were talking about, I saw visibility as the last thing in our previous. Okay, yes. All right. So I remember us wrapping up here. Abstract classes. Define abstract classes at the conceptual level, placeholders. I know I was probably talking at some point, Java's kind of unique that it has an interface, which I think in a lot of times is how people, well, in part define abstract classes that you don't implement, which of course you can do, but also due to the fact that Java doesn't have multiple inheritance or a similar mechanism like Ruby might. But there you go. So we were talking about basic OO things, and the next part there was visibility. So the typical OO visibility things are these 3 levels of interface: public, that anyone can see it; protected, only objects for this class and derived classes can see it; and then private, only objects from this class can see it. As is mentioned here in the footnote, different languages often have different types of accessibilities. Ruby has a slightly different, I can't remember if it's private or protected, it's slightly different than is typical for, say, C++ or Java. I don't happen to remember off the top of my head. All right, and then we'll move down to encapsulation. So why do we have protection here? So data hiding really is part about not exposing your internal data members to outside world, right? And we can extrapolate any kind of hiding. But ultimately, if you don't expose your inner workings and you force your clients to use your public interfaces, then you are free to change the representation at any time, as long as it still does what it's supposed to do, which of course is a plug for unit testing or TDD. Then you can change your implementation without affecting anyone else. And that's, of course, a good thing. Next term they bring here is polymorphism. Without going into what he says, he goes a little bit about the definitions turn many forms. Ultimately, I think polymorphism is the mechanism that gives you the biggest bang in object-oriented programming, where you can treat many things as types of things per all the subclassing that we started to talk here, and of course in the previous book, Pooter, where you end up extracting these classes of things that have the same responsibilities, though they can be fairly widely different. So it gives you the same code and allows you to replace variation through subclassing rather than through sprinkled if statements. All right, so they mentioned in our example here, go to your next classroom. Depending on the student you are, it's different behavior. Review of OO terminology, abstract class. And again, I'm spending some time here because I think this is the foundation that we lay upon all the other stuff. Abstract classes define the set of related classes, what they can do, the interface per se, with the caveat that you're not supposed to instantiate the instance being quote unquote different, but they do the same things pretty much in the class. So concrete class is one that is implemented. He calls out the word concrete for specific non-changing. If we think about student as the generic class that's not implemented, concrete class would be the normal student versus the grad student there. Encapsulation, typically defined as data hiding, but any kind of hiding, information design. Oh, okay. All right, so there. Inheritance, inheriting from the class where you, yes, inheritance from class. You mentioned some or all of the qualities. Starting class can be called the base, super apparent, generalized class. So again, the power of object-oriented programming is through inheritance and polymorphism, where you can typically, when you inherit, you get pretty much all the implementation of the parent class, and you're free to override your own implementation, i.e. you specialize some things there, and so you get code reuse. And this is, of course, the default mechanism of code reuse for object-oriented programming languages. Instantiation is creating of an instance interface like a class, but only provides specification on implementation. So you can see this is very similar to abstract class. You can use interfaces when you want several classes to share characteristics not present in the common class. And again, this tends to be the Java use where you have single inheritance, but you can have multiple people implement interfaces. Perspective is the conceptual mechanism he brought in that he calls from Fowler, the conceptual specification, implementation, 3 different levels of looking at your objects. Term and polymorphism, able to derive different derivations of class in the same way. And again, polymorphism is really about having the same, not exactly his use of interface, but interface as far as methods, which are, of course, are their responsibility. He calls this about speaking of everything as objects. This is actually, classes are an object is not actually true for all programming languages. In Ruby, classes are objects, so it's easy to manipulate them. And metaprogramming is much easier in Ruby. In C++, you can't do that at all, so they really aren't. And in Java, you can do metaprogramming. It's difficult, so to some extent they are objects, but it's kind of difficult. But he's going to narrow the definition to object is considered instance of a class. So now we'll do OO programming in action, and we'll go back and revisit this whole classroom, or not the classroom, the whole shapes example. So how would you do this in an OO manner? Remember, it has the following things to be done. Locate the list of shapes in the database, open the list of shapes, sort the list according to some rule, and display the individual shapes on the monitor. So to do this in OO fashion, he wants to define the object's responsibilities. So this is the classes and the responsibility he wants to have. So shape database, which gets the collection. That was one of his requirements. Abstract shape class has a display, get X, get Y. So location and display here. And then each of the shapes he has, square, circle, they redefine display, they reuse X, Y. Here's a collection display, so you can tell the collection display, which will turn around and display the children, which we'll go down later and probably reveal this is similar to a composite pattern. There's a sort because we had a requirement to sort these, and then display. So I guess display is actually the program that will display these things directly. So now the program is we're making an instance of the database. We ask the database to find the shapes. Via the sorting thing, instantiate a collection that holds all these shapes. He says circles and squares. Main program will ask the collection to display the shapes. The collection, sort the shapes first, display. The collection turns around and asks each shape to display itself. Each displays itself using the display object to display itself. So he alleges that this will help us handle new requirements. He said, well, how will this help us? So if we want to make a new shape, such as a triangle, then we only need 2 steps. We create a new derivation, i.e. we subclass the parent class. We implement the display method for that shape. And then we change the algorithm, sorting algorithm, to handle this shape, which we modify in collection. So the OO approach is limited to the impact of changing requirements. And this, of course, because we revisit Encapsulation is because we hide the details from the user. So now using things is easier because we don't worry about implementation. We've moved the implementation issues to each subclass. So now the caller doesn't matter because we call the responsibility. I call out list call substitution principles, simplified because it's a little more complicated than this, but again, this is just polymorphism. Internals of objects are known by other objects, so we can use them. And again, when we hide this, we reduce side effects because we're not manipulating things directly, which happens if you're reaching into objects in the functional decomposition. If the representation changes, then your code has to change. But now, if you only call them by the responsibility, then it's not the caller's responsibility to know how these things work. So kind of covers that one. And I think this says what I just said. Responsible for their own behaviors, controlling programs don't have to do them. You can change internal to make it transparent, unwanted side effects. So yes, encapsulation is good. So related to this one, encapsulation helps you decouple things, right? Because you don't know the implementation, you can easily replace them without, or add new ones without being affected. So special object methods. So we're going to talk a little bit about object-oriented programming lifecycle, creating and destroying, right? So yeah, I didn't call it here, but this is pretty much life cycle. Constructors initialize or set up an object. So when you make a new thing, you want to be able to do certain things for every object that is in the constructor. Ruby happens to call their method initialize. Other instructors kind of look like the class, like in C and C++, not C++, C++ and Java. He calls out constructors for creation, destructors are finalizers. So I kind of defined what this is, but allows you to, like something that could happen is uninitialized variable, so you can put that in the constructor. You pretty much set up whatever it is that you want at the beginning. Destructors are what you do when the object is collected or destroyed. So typically it's used to clean up an object. In C, C++, C# called a destructor. In Java, it's called a finalizer. For language, the garbage collect, which is probably the main use for garbage collection in C++, not as important. Ruby, for example, doesn't have built-in constructors, but there's at least one gem that allows you to add a destructor. I don't remember if they call it finalizer destructor in that one. But through the magic of metaprogramming, you are able to add such if you want something, but again, cleaning it up. Now, in typical Ruby fashion, we use blocks. So you do like a file.open, and you pass it a block in which you do all the file stuff, and when the block closes, it closes the file, which is, again, a typical use of how you might use a constructor. Or no, sorry, a destructor. But Ruby, having the ability to use blocks, will tend to do that within that. And actually, it could do also an additional initialization in that block. So that's something that's prettier for Ruby and not possible in Java or C++. All right, so the summary is, OO will help us minimize consequences of changing requirements and how it differs from functional decomposition. A review again is functional decomposition, which is our natural way of looking at problems in the real world, which is by breaking down the problem into smaller parts until it's manageable. Requirements always change. Sometimes you just don't even know what they are. They don't necessarily change, but your understanding of the requirements change. Objects are defined by responsibilities, so it takes us to OO programming, where we break things into objects with their own responsibilities instead of just the functions. Constructors and destructors are initialization and cleanup methods unique to object-oriented programming languages. We just covered this. I won't. Attribute is the data in the class. We covered this. We covered this. Derived class are subclasses that are derived from the parent. We covered this. We know that encapsulation is good. Functional decomposition, breaking problems, inheritance, kind of refers to the structure of subclasses. Instance, we talked about instantiation. Member is data or procedure of a class. Method are the procedures for a class. Object entity with responsibility, self-contained. object of data and objects, and OO is often explained as moving the data and the functionality together in the objects. Polymorphism, the key to OO. Superclass is your parent class. Part of me wants to go through the questions, because if you can answer the question, you actually know it. So this is arguably the best part of your stuff, if you force yourself to do that. So I'll put it out to you guys. How deeply should I go through the question? Should we pick a couple that people want to answer? Should I do my usual speak very quickly thing over each? Or maybe I can do a Reader's Digest abbreviation. So anyway, Andrew, tell me.
Let's do all of them.
Okay.
That's my vote. If someone else wants to vote differently,
all right. Here's your chance to veto.
Or endure doing all the questions.
Okay. Okay. Describe the basics of functional decomposition. All right. Should I do it, or should I turn it over to the readers? Anyone? Anyone? Okay. Well, functional decomposition in the beginning is pretty much just breaking the steps down. So, you know, if I were to break something down, like to explain to my mom, I might have a list of directions, like, you know, basically coming up with the algorithm. So the only problem with coming up with the algorithm is dividing up program structure so it's easier to change. That's not really addressed. What are 3 reasons that cause requirements to change? I don't remember what he said, but we can be adventuresome. But I think the big key for this, one, is for anything complicated, you don't really know up front what it's going to be like until you've built it. So, of course, the benefit is after you've built it, you have better perspective on things. 2020 hindsight is really low. The other thing is, as you make programs, because they're not a science, you don't really know if it's good until you see it. And that's why Agile does these very small iterations, so you can get the function out and see whether this is what the user wanted. And a lot of times, maybe it is, but it's not done well. So you have the opportunity to fine-tune things. And then I think in real life, as things change, like if you think of any business, requirements change because, well, for example, in our own world, Slack just bought HipChat. Well, we use HipChat, so things are changing. I bet you competition to Slack will say, hey, they've bought this. What will we do to stand out, to be different from them? So, okay. If anyone disagrees, chime in. Otherwise, I'll move next one. I think about responsibilities versus functions. This more, Al calls out looking at different levels. At the higher level, you think of what things are responsible. When you're coding a function, you tend to think much more detail. What am I passing in? What am I passing out? At a more granular level. Certainly for requirements to design, you want to think about responsibility level, which also helps coax out what the classes are. You think about nitty gritty, oh, I got to like drawing shapes. Well, to draw a circle, here's the center. So then I'm going to put out a diameter and draw a circle around the diameter like you're actually using a compass versus like, you know, drawing a triangle and taking a ruler and drawing 3 things. If you're thinking at detail level, it's hard for you to see that in both cases that might be display. So when you think about responsibility, you kind of coax out the classes and you can think it at a higher level. Coupling versus cohesion. So cohesion is how well stuff belong together. So SRP is an OO rule to help encourage better cohesion, a single responsibility. So if all the methods adhere to a single responsibility, they go together. So a lot of times you have these classes that have multiple responsibilities. They're not that cohesive. And sometimes you have like, you know, what some people call God classes, stuff that just does a whole bunch of stuff. It's not cohesive at all. It's just kind of like you dumped all your functionality in a bag. So coupling is how dependent you are on other classes. For example, in Tutor, we started out with tight coupling where, you know, the guy who rented had to know all about the bikes and the parts of the bikes and, you know, stuff like this because it knew too much detail and it was too coupled. And over time, as we coupled it less, I only had to know about bikes in general. And then, you know, different parts of the bike had different spares. So the bikes used to have to know very detailed parts, but now they knew, hey, I have something that provides spare. I don't have to know the details. So the key word in OO really is loosely coupled and very cohesive, right? The classes make sense. They're very SRP. They're not tightly coupled, so you can reuse stuff and you are less prone to difficulties when you're changing. Purpose of an interface to an object. If we mean the Java interface, which to some extent he's talking about abstract interfaces, we want to know how objects are used. So we expose their responsibilities via the interface and whatever public data attributes, which arguably you want to go away with. And Ruby is unique in that you can only see the data aspects if you expose them through a method, via the various attr things. So Ruby only ever has methods and never exposes the data. Instance is a class, so a class defines for a category of things what they can do. An instance is a unique part of that one. Class, complete definition of behavior object with 3 aspects of an object. Methods are the procedures on the class. Data is what's there, and also we describe. I'm not sure the third object. We describe what it inherits and what the visibility of both the methods and the data are. Abstract class kind of defines at a high level what the responsibility is. In most programming languages that are abstract classes directly cannot be instantiated. Ruby doesn't really have exactly an abstract class, so we don't care as much about that functionality, but we do care about hierarchies. And to some extent, I'll take that back. We'll just leave it at that. 3 kinds of access. 3 types of accessibilities: public, everyone can see; protected, we can see within ourself and other subclasses; and private, only that one can see. Encapsulation is hiding primarily data. I don't know what else you would hide besides that one, really. But if you make everything private and only have methods, then no one knows your implementation. And per our shape object there, everything does a display, so I don't have to know how a triangle displays versus a circle versus a square versus a pentagon. Polymorphism, again, is the ability to call different things through the same interface. So all shapes support display, and the collection supports display. And again, we see that's the beginning of the composite pattern. 3 perspectives for looking at object. Oh God, what were they? Conceptual. They were up like here. I gotta go back and look because it's not top of my head. Boom, excuse me. It was like conceptual specification and coding. I don't know if that's exactly the words he uses. If anyone has found it or recalls, but that's a 3 level. The conceptual, the specification, so very high level kind of design level, and the nitty gritty data level, where you're actually coding and comparing about the details. Okay, so boom, 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 boom. Interpretation. Sometimes programmers use modules to isolate portions of code. Modules, aka also known as packages, also, I think that's what he means by this word, or namespaces. That's always good. Ruby guys learn to use that more as their classes use bigger. Java kind of forces you to do that from the beginning. I think that's what he's talking about. This is, of course, good. Anyone have a why not? It's not alone strong enough. If you use the other parts of object-oriented programming, particularly polymorphism, encapsulation, that helps. But for example, I think, I hope I'm using this right, because that's what I think of modules when I think Ruby interfaces. So if someone can think of another use of that word, maybe we have a different answer. Is it too limited to define abstract class as a class that doesn't get instantiated? Why is this too limited? It's limited because that's not the prime benefit. And again, in Ruby, since we don't have abstract classes, we don't care so much about that one. The key part of the abstract class is defining at the highest level what the responsibilities are of the subclasses, i.e. the interface for this family of objects. How does it help limit the impact? Because you don't know how things are implemented, you can only call the public interface. And so internal data algorithms and representation can change, and you won't know. And because you don't know, and it's self-contained, side effects are less likely to happen because it's all self-contained within the objects. How do interfaces protect objects from changes that are made to other objects? Because if your interface doesn't change, kind of the same as above. 3 and 4 are almost the same answer to me. A classroom is used to describe objects in a system. Describe this classroom from the contextual perspective. I don't know that I understand the question. Anyone? Yeah. Does anyone understand what he's saying here? Okay.
Yeah, I'm trying to understand it.
I don't understand it either.
I almost think he wants us to describe a classroom as objects, which I might have a room and teacher and students and subclass. And the teacher will tell people to like work, stand in the corner, go to your next classroom. Which you can imagine the...
Oh yeah, probably like you use the classroom as a metaphor.
Yeah, maybe the the smart student work is be real effective, and the slacker student work is like do something and then get on his phone, then do something and then surf YouTube. All right, that's my best guess on that. Opinions, applications, changing requirements is one of the greatest faced by system developers. Give one example. I don't know. You guys can give examples. Our requirements change all the time. Like we redesign our website
That never happens.
every half year or so. So actually, I don't know that it's because of changing requirements, but there you go. I think everyone, I don't know if we say this, stuff always changes. Fundamental weakness when it comes to changes in requirements. The weakness in functional decomposition in my mind is because it doesn't force you to organize things in a certain way. And that's where lack of encapsulation hurts you. What do you think is the best way to deal with changing requirements? There's a whole methodology called Agile that works for that one. So obviously good coding practices, setting up a methodology in which you can learn. Cleaner code, the better. Be flexible. Valium, so that you don't get too angry when things change on you. Okay. By the way, no one on this team uses Valium. That's a joke. You never know. I've probably offended somebody, and I'm a bad person now. So sorry about that. All right. So that covers chapter 1. If there are any questions before we move on, we can address them now. Otherwise, we'll move on to Scott and let him present. I realize I didn't pick to present everyone, but there you go. So if there are any questions now, speak. All right. Then I will stop screen sharing and I'll turn this over to Scott. Scott's picking up chapter 2, UML overview.
All right. Can people hear me?
I can.
And it sounds okay?
Sounds reasonable.
All right. I'm hooked into my speakers, which if I unplug my speakers, the sound is still terrible. So I'm glad it's all working. Okay, the UML, the Unified Modeling Language, this is something that I was heavily involved in years and years and years and years ago when they attempted to use it almost like visual programming. And those who were around in those years know that it finally sort of fell apart. They could never actually get it to work that well. Lots of technical issues and just it was not something whose time had come. However, the aftermath of that is that the UML has been a really good tool when you just want to discuss how to design something. And so they cover UML in this book as a useful thing to know, but you only need to know a very limited amount of the UML for this book because we don't need much of it to cover the design patterns. So that's this line here. So we're going to cover a subset We're going to talk about what the UML is briefly. There's not much to talk about on generally describing it. And then we're going to look at two of them that are really useful, the class diagram and the interaction diagram, which will actually end up being the sequence diagram. So what is the UML? It is a system of many kinds of modeling diagrams. I like his use of visual language. And what it does is it creates models of programs, and it presents different presentations of those models depending on what you're trying to communicate. Okay, so the UML has several different diagrams, some of them for analysis, others for design and implementation. So he goes through and he talks about different kinds of diagrams, and then he says, these are interesting, but we're not actually going to use them. So when you are in the analysis phase, he likes use case diagrams, which involves interaction with things outside of the system, the technical system, say users or other systems, and the function points that you need to implement. And then activity diagrams, which focus on the workflow of the problem domain. These are basically getting together the requirements of what does the system have to do, rather than actually implementing the logical flow of the program. So that's about it. He's not going to cover those much in the book, or at least he claims he's not going to. So looking at object interactions, he will ultimately talk about the sequence diagram, which is the most popular of what they call the interaction diagrams. And then in the design phase, we're going to cover class diagrams, which nicely detail the relationships between classes. State diagrams, which talk about the different states an object may be in and the transitions that cause those different states. I think he claims he's not going to go into that very much. And then in the deployment, this is how stuff gets deployed, and he's not going to talk about that anymore. So really, all we need to worry about in this chapter are class diagrams and sequence diagrams. Why use the UML? It is a communications device. It's used primarily for communication with yourself, with other team members, and with customers. And it's useful because it has a methodology about how to organize and present the requirements in such a way that these other members that you're interacting with will be able to understand in the same, much closer to the same detail that you have, or you will be able to understand much more closely to the presenter who is trying to communicate these requirements. One of the ways it does that is it does it for clarity. And so the really nice thing is you can get checks with the other members of the team whether the system is understood the same way by them as it is for you. This becomes important because systems are complex. Okay, and then for precision, it helps you not miss details. So it's also a good design tool because it forces the designer to think through the interrelationships between the classes. And then the sequence diagrams will help him find that out also. Okay, the class diagram. This is the core of the organization of object-oriented programs. It describes classes and shows the relationships between them. Following types of relationships are possible. And here we start talking about what we've already learned in the previous chapter. If we have an is a relationship, we've got probably an inheritance. And then when there are associations, whether it contains or uses or creates another class, all these are different ways of establishing associations or relationships, and the UML will have different ways of displaying those. There are variations on the themes. I find this gets to be a little bit of a little bit tangled up in this chapter. One of them is composition, the other is aggregation. A term that I've heard used more for aggregation is association, and that I think I like association better, but I got to go with his. Okay, so before we show the relationships, we have to show the class itself. And there are options as to how much you show depending on how much detail you want to go into. The first one is to just simply show the name of the class. In the left example, it's called square. And then you can show the data members of the class, which is display. And then you can show the methods of the class, which is the methods that you can attribute to it. This is a very interesting reversal of the way I learned, and that was I learned that you probably came up with the methods first, and then that would help establish what the data needed to be. So it all depends on what you're trying to communicate. Okay, so some details. The punctuation in front of the entry into the class diagram basically defines scope. And that is it publicly accessible? Is it private to the object itself, or somewhere in between, like protected? Plus means it's public, minus means it's private, and then the pound sign, we'll find out, is used for protected. And here we cover those. Okay, so the UML notation for relationships. You can have aggregation, which means which uses this clear diamond here. I'm sorry, this non-filled in diamond, and that says that it uses other objects, but unlike composition, it doesn't own them. In composition, it actually has these, and as having them, the implication is that if the object at top goes away or is destroyed, then probably the objects that he's associated with in composition will be deleted or go away also. Inheritance indicates that the subclass is a version of the main class. And then lastly, a dependency also uses something else, but it's at a much higher level of interaction. So this object depends on this other object, but how it depends in this line is sort of unspecified or generic. Okay, so a class can have several subclasses, as in this points out the example that we had in the previous chapter of different graphical elements having all being a shape and having very similar methods to display them in particular. Okay, the notation is that if a class name is italicized, then that means it's an abstract class. And that can be used in Ruby to imply that it sort of acts like an abstract class, even if it can be implemented on its own. Okay, as they say, as it says, it can be used to largely define the interface for the classes that derive from it. It can be a place to put commendated methods. Or the abstract class may define methods that are required to be implemented by the subclasses. So it shows the first example of the has-a relationship. When it's aggregated, then it does not actually own the members in the association or in the aggregation, but it does have a close tie to it. Okay. I think the author observes kind of that aggregation introduces some ambiguity between has-a and uses. In other words, an aggregate relationship versus a dependency relationship. And I think this is instructive. He notes the ambiguity with the use of interface for different meanings. And so what it leads me to believe is that this whole thing of class diagrams can tend to be a little bit in the eyes of the beholder. In other words, an organization may apply these a little bit differently depending on what their requirements are. Okay, so then he notes that an aircraft can be a jet or a helicopter, meaning that a jet or a helicopter is a kind of aircraft, so is inherited. The aircraft is an abstract or an interface. So an airport can treat them the same, a jet or helicopter, the same as an aircraft, and so it is it's useful. It shows the polymorphism. Okay, the other type of relationship is the containment means the contained art is a part of the containing object. Composition is what it's called. And here is an example. A car that has tires. If the car goes away, the tires go away with it. On the other hand, it has a dependency on a gas station. But that dependency is very high level, and it's not going to investigate the same level of business rules on the gas station as it would with something in a more classically aggregate relationship. Okay, so we've covered this. Aggregation means the aggregated objects are not inherently parts of the main object, whereas in composition they are. In composition, you're probably going to have constructors and destructors to help with the management of those objects in the composite relationship. So at the next more detailed level of expression, he introduces the notion of cardinality. So not only can we know the aggregate or composite relationships between these different objects, but we can imply, okay, here are the limits to the numbers of objects that can be aggregated or composited. So here we have an aggregate relationship, and it's saying basically that an aircraft can either have an airport or not. Interestingly, observe that the cardinality is at the opposite end of the object. So here, the aircraft can have 1 or 0 or 1 airports. The airport can have 0 or more aircraft. Notice there's no cardinality expressed for dependencies. So hence, if you don't have cardinality, it may be a clue that you want to use a dependency instead of an association. Okay, a car composite has a tire. It can have cardinality. A tire can only have 1 car, but a car can have 4 or 5 tires. Where if it has 5 tires, it's probably the 5th tire is a spare. And then he says, okay, also remember, you can have notes if the relationships have a degree of ambiguity and you want to put a little clarification into the ambiguity, you can use a note. A note is basically a, looks like an envelope with a corner folded over. So when you see that, it's a note. So here he goes through and explains what I explained. And interestingly, if cardinality is not specified, no assumptions made as to how many objects there are. Hence, you may want to use a dependency, use the dash line instead. Okay, that's it for class diagrams. We'll go to interaction diagrams. And for all practical purposes, all we're going to cover is the sequence diagram. So class diagrams show static relationships between classes. They don't show us any activity. You really kind of want to know frequently. As a matter of fact, I find that I use sequence diagrams more often than class diagrams. You want to find out, hey, what's the sequence of messages between objects? So we have that down here on figure 2.8. And you can think of it as a graph. The objects are horizontal. We have objects main, a shape DB, collection, different names up at the top. These define objects, and these are typically instances of classes. And here, main is probably the most parent code or class. The vertical graph works as time, and time starts at the top and descends towards the bottom. And what you encounter is, as you go in time, you encounter messages. So the very first message is message in time. In this example is get collection. And main is sending a get collection message to the shape DB object. And the shape DB object in turn is going to send a message, instantiate to collection. And so that instantiates the collection. Now it can go on and can say, okay, instantiate me a shape, a square shape. And now what he's going to do is he can say, add that shape that he got up here, add that to this collection down on number 4. And then in number 5, he's going to instantiate a circle and retrieve that and add that to the collection on message number 6. And then main can retrieve the selection using the return collection message, which would be sent from the shapedb back to the main routine. Then below there, this shows some global things that can be done. So for example, on message number 8, sort shapes, it can ask the collection to sort the shapes according to whatever criteria is needed by that. And then at the end, on number 9, the last thing the main program does is it says, okay, display the shapes, and the collection will roll through itself and tell each of the shapes to display itself. So, so that might be for each line, display the shape, and the display routine for that shape will know how to display it, and then it will do another display. And this is confusing to me. So I'm going to abort that and go on. Okay, so sequence diagrams, as I've said, are read from top to bottom. Each object at the top represents a particular object, and some of the objects at the top may have a colon in them, and that may indicate that it's the word before the colon is the object name. The word after the colon is the class that the object is an instance of. Vertical lines are called the lifeline of the objects. And some UML programs don't support this, so you don't really know when the object is instantiated or destroyed. So objects are shown sending messages with horizontal lines, and that's kind of a review of that, of what I talked about before. Sometimes returned objects or returned values or objects are explicitly shown, and sometimes it is just understood that they are returned. And that is where I think I made a mistake. And then this return that is where this is, in order for this get collection to work with this shapedb to return the collection, the get collection is going to have to pass the main routine so that the shapedb knows how to send a return collection back to it. All right, so we went over this stuff already, and we're getting close on the end of time. So the rest of the, so let's go on. The summary, purpose of the UML is to flesh out your designs and communicate them. Don't worry too much about creating diagrams the right way. That comes with practice, and your group will gain conventions for it. If your diagram doesn't communicate adequately, you have an opportunity to use a note to enhance it and go for clarity. Don't use the UML in non-standard ways, and just consider what you're trying to communicate as you draw your diagrams. The last thing I'd like to do is to, wait, on this one here. Is I've got references in this meeting notes on the comments. I use this very nice BRAMP JavaScript sequence diagram generator as a very simple DTL for it. And it updates as you edit the DTL, and it does a really good job. Highly recommend it. And then I haven't done anything with this, but it looks very promising. This has all the other UML diagram editors, and they're free, and they're unlimited, and they're not limited, and you may want to look at that. And it shows quite a few enhancements to class diagrams that I had forgotten about. That's it. It's 11 o'clock. Forrest, I'll turn it back to you.
Yeah, thanks, Scott. So it is 11, so we'll wrap up. I think next session we'll pick up and we'll do the questions, because I think the questions are valuable. Quite possibly, if someone who's not the presenter does the questions, then there will be some forced learning done there. So I just need a volunteer who wants to do chapter 3. Chapter 3 starts a new section of limitations of traditional object-oriented design, and it's called a problem that cries out for flexible code. So it's a CAD/CAM example, talks about the problem, looking at the space. I think it's all domain problem and some basic classes. Yeah, I think one chapter enough should do it, especially if we get to the questions. So who wants to volunteer for chapter 3?
I'll volunteer.
All right, Andrew will do chapter 3. I will see you guys in 2 weeks. Thank you for coming and listening to Nested Loops. Have a good day.
Thank you. Bye.
Bye.